Okay, so this is the Excel file as you received it. When you open the file, this is exactly what you would be seeing. On the right-hand side, you have this chart, which contains a schematic depicting a producing well in yellow here, a set of perforations into the producing reservoir, and these green arrows that depict the flow into the producing well. Now, what we have here is the pressure profile in blue away from the well. And then we have two additional series on the chart. One is in green, which depicts the drawdown, that is the pressure difference between the initial pressure, this value here, and the bottom hole pressure at the well location. So that is the drawdown. And then in red, this horizontal line, which represents the investigation radius. Okay, so this is nothing more than a simple Excel chart with these three series: the pressure profile, the drawdown, and the investigation radius, and then a couple of simple drawings on top of the chart. That's all it is. Okay, so the idea here is for you to be able to quickly observe the impacts that each parameter has on the pressure profile and the drawdown and radius of investigation, of course. So for example, if we want to see the impacts that permeability has, we go to the scroll bar here at top, K for permeability, and then we can simply drag and observe in real time how the profile changes with that parameter. Now you can drag that bar or you can click on these arrows to move one step at a time, right? And then you can test your intuitions. So the lower the permeability, look at the drawdown in green, the smaller the permeability, the deeper the drawdown. Small permeability, deeper the drawdown because you need to create a higher delta P to produce the same rate. Conversely, the higher the permeability, the narrower or shallower the drawdown needs to be to produce a certain rate. With the investigation radius in red, the smaller the permeability, the less you can look into the reservoir, the higher the permeability, the farther into the reservoir you can look. Let's test porosity, which sometimes causes some problems in people's intuitions. So for example, let me just create some room here with the permeability. Let me just leave it there so you have enough room to play with the porosity. So the smaller the porosity, look at what happens to the investigation radius, the farther into the reservoir I can look. Why is that? The reason is because the smaller the porosity, think of it in terms of the pore volume. The smaller the porosity, the smaller the pores are. And when the pores are small, the information that travels through the pores gets to the next pore faster. Okay, so the smaller the porosity, the faster the information travels. So the farther I can look into the reservoir. And conversely, the higher the porosity, the less distance I can travel for the same rate in the same time. The viscosity again is fairly intuitive. The smaller the viscosity, the lower the viscosity, the thinner the fluid is, the easier it is for the fluid to flow, the narrower or shallower the drawdown needs to be, and the further I look into the reservoir. The higher the viscosity, the thicker the fluid is, takes more effort to flow, therefore I need a higher or deeper drawdown, and the less I can look into the reservoir. Okay, now in terms of rates, again, fairly straightforward. The higher the rate, the deeper the drawdown. But notice how the investigation radius doesn't change with the rate. This is one of the key principles in pressure transient analysis. Rate does not affect the distance or the investigation radius. Okay? And time, initially we're there. We put the well on production. Let me just create a little bit of more room there. Put the well in production, and as the time passes, your pressure profile travels farther and farther into the reservoir. Okay, so both drawdown and investigation radius increase over time. Okay, eventually you will reach the tank boundaries and the whole thing transitions into pseudo steady state and the whole profile now moves downwards as a whole. Okay, so where is it that this chart is getting the data from? Just for you to be able to actually edit this at will using your own ranges or your own set of parameters. So you need to go here to the data menu option, and then you need to, sorry, to the view, and then you need to unfreeze. Okay, now you access the entire sheet. So what I have here at the top is the diffusivity equation resolved in radial coordinates. This is the infinite acting radial flow formula. And this is taken from the DDA book by Kappa, which is actually free, available on this website here. So I'm going to move my browser window across, and this is what you would see, DDA book. You can actually download the PDF, or you can also read it online. Okay, and when it opens, you have this menu at the left. You can go to the theory to find line source solution in homogeneous infinite reservoir. You can go through the whole derivation process. Line source solution in radial coordinates, and you notice that that is exactly the formula that I'm pasting into this Excel sheet. Okay. Initially it was without skin, and then skin is added in derivation. I'm also bringing snapshots of the investigation radius formula because I'm going to use those two to build the series that I'm bringing to this chart. Okay. Having these formulas up here, all I need to do now is to implement them. So what I've done here is I've hidden everything, every calculation to create these charts is sitting on this sheet, but in white fonts. So let me just make room. I'm going to move this chart to the right. I'm going to go to the developer tab, design mode to activate these scroll bars. I'm going to move them to the right to uncover what I have sitting under it. And below here, I'm just going to select and I'm going to put a black font so you can see what I got here. So this is where the magic happens, right? So on the first column, I have the distance radius, which is the x-axis on my chart. And on the vertical axis, I have the pressure, which is calculated for each distance at any point in time. Now, these are numbers. Distance, I just ran from an initial value to a final value. And these are just numbers. Okay, didn't grab there. From an initial number to a final value, as I was saying. Okay, and then the pressure is the formula which comes from that equation. I don't know if you are aware of this. Many people do not know this trick, but you can name cells in Excel, which makes it for a much easier auditing process. So for example, this cell, so permeability, I have a K label in column B, row 19, but the value is held on this cell, which typically would be referenced in formulas as C19. But in this case, I'm naming this cell K. You can name any cell by typing something in this box here. So for example, if I put any number there, let's say 46, and then I hover over this box, which is referencing to E15 by default, I can just click on it and rename that cell with whatever name I want. And now I can reference that cell by its name. So H plus 1. See? It's much easier to audit formulas when you have cell names instead of the default Excel references. Okay, so I have named all these cells, and you can audit yourself the formulas that I have here. So you can go item by item, term by term, making sure that this is exactly the formula that I have implemented in this cell. I have added an if statement to make sure that there is no crossover. That if statement means when this value calculated by this formula is higher than the PI, initial pressure, cap it at that initial pressure value, just to ensure the continuity and there's no crossover above initial pressure. And the other thing that I have here is a valid flag column, which tells you whether the calculation is valid or not. If you go to the later, to the farther distances, you would see these no's here. And the reason for that is because the solution of the diffusivity equation, you can see in the book, if you don't know already, is a complex exponential integral function, and that can be approximated by this simpler expression with these log terms when that time value is higher than this term. Okay, so I have added this flag, but this is just for visibility. I'm still opting to use this formula for the entire pressure profile, again, just to ensure continuity, and I don't want to make my life complicated. I'm not using this for precise calculations of pressure values or to construct a very precise pressure profile. All I want to do with this tool is to quickly assess interactively with these sliders the impact of each parameter. Okay, so I'm not going to get too fast about not being too precise. So once I got this, then I have everything I need, distance and pressure, to build that pressure profile. And then on the right hand side, I have these two blocks, which I have built for those two additional series. The green series, which is the drawdown, so that is highlighted there, and the red series, which is the radius of investigation, up there. So I've built this. Obviously, these are simplistic 2-point straight lines, each of those. These are vertical straight line, this is a horizontal straight line, and those three are the series that I have in this chart. Now, this chart, I'm going to create a copy of it just to demonstrate the fact that it's nothing more than a simple line chart in Excel with some drawings on top. So these are just drawings that I can eliminate, and then I can bring back the axis. So you can see this is a simple, regular, good old Excel line chart. Okay, these are the vertical axis. These are the values that I have selected to create this profile here and to play around with these tools, but you can obviously customize these to the values which are more suitable for the projects you work with. It doesn't really matter. Again, I'm not concerned with the numbers at this point. All I want is to see visually the pressure profile and the impact that each parameter has with this interactive tool. That's all I'm doing with this tool. Okay. And the other thing that I can show you here is if you can go again to the developer tab, design mode means you can actually select that element, and then you go on the properties window and it tells you that scroll bar is linked to cell C19, which is the K value. You assign here the range, in this case between 1 and 200. So if you go away from the design mode, that means the lowest value is going to be 1 and the highest value is going to be 100. That's how that slider or scroll bar is going to operate. Okay, so you can do the same with each scroll bar. Just go on design mode, select and change the properties if you want to link to a new cell or change the range of that scroll bar. Okay, so that's pretty much it, guys. You can grab these and edit at a will and let me know if you run into any problems. Enjoy. Cheers.